Okay, here is a full solution of Ryden 9.1. And as we get into this, I want us to remember that the sort of basic timeline of BBN looks something like this. At early times, there is chemical equilibrium, more or less, between protons, neutrons, electrons, and neutrinos. And at a time of about 1 second, the weak interaction freezes out. So that happens at about 1 second, and it occurs at a temperature, or if you like, a characteristic energy of approximately 0.8 mega electron volts. And that means that roughly the ratio of neutrons to protons remains more or less fixed at that point, but can further evolve not from those weak interactions that were keeping the chemical equilibrium, but can evolve due to the fact that neutrons can decay. I guess that is a weak interaction process, but also that neutrons can interact with protons and turn into heavier elements. But those heavier elements have to first go through deuterium. However, deuterium can't be produced in large quantities because it can too easily photodissociate from all the high energy photons in the background. So the universe has to evolve a little bit longer to the time of what we'll call nucleosynthesis, T-nuke, which is on the order of 200 seconds. It's actually a little bit less, but that's the order of magnitude. And right, there's a characteristic temperature for that as well, but is not needed to do the calculation. So these are kind of the two goalposts, or the two milestones, or the two milestones that one has to get through as we ask what happens, how do the light elements get produced. Okay, so that being said, what we're interested in this problem is something called Y, specifically Y max. So remember that Yp is defined as the ratio of helium-4 to the ratio to all the baryons in the universe. And this is a number that has been measured now at the percent level, and we'll go into a little bit more detail about this. But at the very least, one can, based on fairly general, fairly simple arguments, argue that the maximum helium mass fraction, Y max, should be given by 2 times F divided by the quantity 1 plus F, where F is the ratio of neutrons to protons evaluated at T-nuke, at the time of nucleosynthesis. So in this particular problem, you're trying to see how does Y max change if the lifetime of the neutron changes. So that being said, what we should keep in mind is that, so if you like, what we're trying to do is figure out what this ratio is. This F is defined here at this time. And what we're given from, well, the physics of the weak interaction is the ratio of neutrons to protons at the time that the weak interaction freezes out. In other words, this is something that we're given here. And the question is, really, how does that fraction, that ratio, how does it evolve from the time of the weak interaction freeze out to the time that nucleosynthesis begins? How does this occur? And this is what I'd like to clean up in this video, in addition to giving you the solution. So, since we get to neglect all the interactions except for neutron decay, basically neglect everything except for the fact that neutrons decay. So neutrons turn into a proton plus an electron antineutrino. So example, things like neutron plus proton goes to deuterium plus photons. Yes, that's occurring, but not at high rates, at least not until nucleosynthesis occurs at T-nuke. So we will not worry about that. So what that means is that the evolution, if you like, the evolution of the number density of neutrons happens because neutrons decay. And the way that that looks like at this particular time is that the number density of neutrons, whoopsies, it will evolve because the universe is expanding. And so what I'll do is indicate Number density of neutrons initial, and that initial point will be the time that the weak interaction freezes out. This is divided by the scale factor cubed because, right, the universe is expanding. But this gets multiplied by an exponential decay factor, e to the minus t over tau n. Okay. At the same time, remember, since neutrons decay into protons, that means if your neutrons are going down in abundance, then your protons should be going up in abundance. And the way that that should scale is like this. Your protons by themselves start off with some initial value, and that goes down according to the because of the volume expansion. But then there's an additional term, which is that due to the fact that these neutrons decay, however many neutrons have decayed, that goes into a proton. So this factor here needs to be the number of neutrons that have decayed so far. This, if you like, this is the number that remain. Therefore, the number that have decayed would be the initial value minus the leftover value. Okay, let me just write this down and we can verify it rather than trying to derive it. This term should look like n naught, a factor of 1 minus e to the minus t over tau n, and then this all gets divided by a cubed. Let's see if we can verify this then. If this is true, then that means that when a neutron decays, it turns into a proton, so that the number density of neutrons plus the number density of protons should be a constant modulo the fact that the universe is expanding. So let's just check that real quick. In fact, you can probably do this on your own. This factor with e to the minus t over tau plus np naught over a cubed plus this term, and you can probably see what's going to happen. That the exponential term will cancel. This one cancels this one. And what you're left with is simply np naught plus nn naught all over a cubed. And so that means that you don't lose any baryons in the process. So this appears to be the correct form for the time evolution of the number density of neutrons to protons. Again, np naught and nn naught are the number densities as established when the weak interaction freezes out. Okay, then we're ready to move forward. The fraction that we're interested in, again, which is the number density of neutrons divided by the number density of protons when nucleosynthesis occurs. In other words, this is, we're going to use the formula we just wrote down, nn naught over a cubed times e to the minus, the time is when nucleosynthesis occurs, and then divided by the initial number density of protons plus this factor with the 1 minus e to the t nuc over tau n, and all of this is divided by a cubed. So you have an a cubed in the denominator in the top and the bottom. So that's what f is, and now let's clean this up. Clean by multiplying by the top and bottom by a factor of, let's do it like a cubed divided by n naught to top and bottom. So in doing that, you will hopefully conclude that this looks like e to the minus t nuc over tau n. Again, I think by now you know this. Tau n is the decay time of the neutron. And then this is divided by the fraction np naught over nn naught plus a 1 minus, I'll put these in parentheses for fun, e to the minus t nuc over tau n. That would give you your expression for f that can go into your expression for y max. The last thing to point out is perhaps a reminder that the statistical mechanics that we sort of glossed over tell us that this ratio of the number density of neutrons to protons at the time when the weak interaction freezes out is very approximately, and it's a very good approximation given by the exponential of minus Qn over K times the temperature when the weak interaction freezes out. As a reminder, Qn is simply the mass difference, actually the rest energy difference, if you want to say it that way, between the neutron and proton, and K T weak is approximately 0.8 MeV. That works out to be approximately 0.19, or basically 0.2. And when you plug that in here, this ratio, that's the opposite of that. This is approximately 5. And there you go. What we've just done is we have sort of reestablished Ryden equation 9.32 in slightly more generality. Okay, so that means to actually solve this particular problem, Ryden 9.1, the book problem 9.1, has you doing all of this stuff, but let the decay time of the neutron be about 10 times shorter. In other words, make this 88 seconds. I think it would be good for you to plug in all those numbers. You would hopefully find that the consequence of doing that is that this fraction of neutrons to protons at the time of nucleosynthesis would be a tiny number, would be approximately 0.175, taking it to 3 decimals. And as a consequence, this would tell you that the maximum amount of helium that could be produced would be approximately 0.034, or about 3.4% of a mass fraction. And that would be your final answer.